Um, uh, okay, so topic today um, is about algorithmic statistics, and there is a paper from 1 year ago that uses the theory to cluster functions. So the application is on the MNIST data set. And so when MNIST data set is a very old data set, and now it can be perfectly classified. If you even, so there are like 70,000 pictures or something with handwritten data. It's in all machine learning handbooks, they use this data set, for example. So I assume people know this data set. So, but now the task is harder. So can we cluster the pictures? So, the task is take 100 random pictures, evenly distributed over the classes, and then find clusters of 10. So first find the right cluster number. So even if you take fewer than 10 pictures, can you always understand that there are some number, let's say k between 1 and 10, well 2 and 10, that there are k classes, and can you put the pictures in the right class, but without using the labels. So this is a harder task. So this you cannot do with 99.7 or whatever is the record on this data set. And so you have much small, so the number of examples is limited to 100, and you need to not use the labels. And so 1 year ago, there is a paper that uses ideas from algorithmic statistics to solve this task almost perfectly. So a number of mistakes really small. Unfortunately, this algorithm, I was reading it today, but there is a step in the algorithm that makes no sense to me. So I will not speak, unfortunately, about this algorithm. And also there is, so Hinton, he received Nobel Prize for machine learning. I don't know anything about this, but he has also a paper about using MDML principle to select weights in neural network. And he uses MDL theory, its minimum description length principle. And this is very closely related to algorithmic statistics of today's topic. But I checked this paper and it is kind of like trivial application. So he create a mixture of Gaussians and then say if we take the, so he creates probabilities from some basic distribution. And then he says if we take logarithms, we interpret it as description length and we apply MDL principle. And so there is nothing unexpected going on there. And I guess he then argues that it somehow works, but the experiments are very small. So there is 1993 paper, and it was advertised by Ilya Suchkever. He is from OpenAI, and I was given a list of papers to check and perhaps mention in the course. And so this paper I found because of this list. So, but okay, I don't know what to say about this. So just okay, we try to compress the weights by assigning probabilities. They're Gaussian, so we have continuous probabilities, but you can always put them in bins or just ignore because you're tuning parameters. So the rule is just assign probabilities to everything, but using Gaussian distributions, and then take logarithms and then log probability. He says it's code length, but okay, well, what is new? I don't understand, except some layer of message length and sending. Okay, so but also I admit I read very quickly. I will read it again, and I need to make a so this lecture I will also give for Huawei company in a few days. So I will read the paper again. Maybe I understand better that there is something non-trivial. So I will just, so this is where came the idea of today's topic, but the topic is very interesting theoretically. So the question is, if you receive a bunch of information, how can you abstract a model? But it will be seriously simplified. And so normally there is a lot of background information and you only want a model that model a part of the data. But we will just think about a case. We have a machine that produces a string, zeros and ones. It says here I'm finished. And our task is find the probability distribution that somehow incorporates all the regularities in the string. So so let's go back to the beginning of the definition of Kolmogorov complexity. So imagine we receive some strings of ones, and we see that all the odd bits are 0, but in the even bits, oops, we don't see any structure. Oops, again wrong. Like this. Let me take a better marker. So the even bits, they look random to us. Okay, I should make a much longer, but you got the idea. But we see in the odd bits somehow 0. And so a good model after we inspect this would be like, okay, fix odd bits and fix 0 in odd places and take the uniform distribution in even places. And so task is given one single string. What could be an optimal model for it? Yeah, let me take the pen for today's lecture. I printed the seminar. So the first question can be, okay, There is a question. Okay, imagine we already fixed a model. How can we score the model for given string? And one way to do it is to use randomness deficiency. So the idea is we will use prefix Kolmogorov complexity for the definition, but all the theorems that I will switch will have logarithmic precision. So don't worry about the prefix version. So we could say that if we have a string x, so probabilities will always be over finite sets of strings. So that means we have a bunch of rational numbers and a list of strings. So we can encode P as just a finite string. So when I write P inside Kolmogorov complexity, just think about a finite description. And we say that if Kolmogorov complexity, so we could measure, so we could say if just arithmetic coding or finite coding gives us an optimal way to describe the model, then this would be close to zero. And so if this value is small, that means that if we compress x using this probability, then we will have optimal compression. And so we could say that randomness efficiency of string x given model P is defined by this quantity. So we know that Kolmogorov complexity also has a definition with universal measure, Lauerstein, optimal Lauerstein computable measure. So this could also be seen as the logarithm of x given P divided by P of x. And so if universal measure is close to the assigned probability. And so first proposal, and this is Kolmogorov's original proposal somewhere in the 70s. He gave a lecture. He was already old by that time and he had Alzheimer. So, but still an important idea. He says that the best model to select from string is the P with smallest Kolmogorov complexity, for which this is smaller than some prescribed constant. And so he says that so he defined the notion of alpha beta stochasticity. So he says that string x is alpha beta stochastic. Okay, so this is defined as randomness deficiency for the model P. So there are two possible definitions. So this is equal to plus of 1. And so x is alpha beta stochastic. If there exists a measure P of complexity at most alpha, for which the deficiency is at most beta. And if there exists P with A of P bounded by alpha and the efficiency of x given P smaller than beta. Okay, so I should have waited a little bit before giving the definition. Let us first think about the properties of randomness deficiency. Imagine that we go in the other way around. We have x and we want to use it to find P. Now imagine that we generate some x from P and we check what is the probability that deficiency is big. So my claim is now that we can view deficiency as kind of statistical test. The probability that deficiency is bigger than some value d is bounded by 2 to the power minus d when we generate x from measure P. So let me write it. So observation probability of all x so that dx of P is bigger than some value. Okay, let's call it E. is smaller than 2 to the power minus. So how can we, this little lemma, how can we prove it? Why is it true? So for this, it's better to use the second definition. So sorry, I should be say big O of 2 to the power minus. So so we have to check the probability that we sample some x for which m of x given p divided by p of x. So let me write it as a sum. So we have to look to the sum of p of x for which this is bigger than 2 to the power. So so is it clear why this is smaller than 2 to the power e minus e? And so when we sum over all the x's, okay, so imagine that here we have a set of x's that satisfy the condition. And so imagine that we just have this set S is a set of all x's. For which mxp bigger than 2 to the power e of x. So when we sum p of x for x in S, so the just p of s. But by definition, this is bigger. So this is smaller than 2 to the power e m of s given. Right? Oh, so it's too low. You cannot see it because of the compute reg. Did I write it correctly? I should say 2 to the power minus e m of s. And now it's clear, right? So this is bounded by 1 because it's probability of s. And so p of s must be smaller than 2 to the power minus e. So randomness deficiency is only high with small probability when we generate from the measure. So we can say that this randomness deficiency test. For example, here we have our model with zeros in odd places. Imagine that we have all zero sequence and the sequence is length 2n. Then we know that this is very special string and we believe in it with probability roughly order 2 to the power minus n. Because we got a string that has all one description. Randomness deficiency will be maximal for the all zero string. So in our model, so we have 2n zeros in our model, the string has probability 2 to the power minus n. But complexity of x given p, or just complexity of x, is log n. Okay, a little bit less. So yeah. So we have in this example we have n minus say 2 log n. So complexity is bigger than plus of 1. And so if we say all zeros, then the significance of our test will be 2 to the power n. So we reject hypothesis that the hypothesis of being random in the even positions. Okay, so this is a statistical test, and this is motivation of randomness deficiency. Okay. And so Kolmogorov's question was, can we find for every string a simple model? Is the first question. So is it true that for every string x, there is a reasonably simple model? Because if we want to use this definition for extracting a model, then it would be bad news if all models are bounded by O of one constant. And so Alexander Chen then was in the lecture where this question was asked, and he solved it the next day, and he wrote paper. So he is one of the books in the reference he wrote. So the Kolmogorov's question is it true that every string x is alpha beta stochastic for reasonably small alpha and beta? Beta is significance. So beta is the bound on the randomness test. So we need to tolerate. Alpha is a complexity of the model. And so it was, it turns out to happen that whenever alpha and beta is small, alpha plus beta is smaller than n, there exists a string that's alpha beta stochastic. But first, let us view that, let us understand what are the trivial things we can say for any string. So every string is oops, sorry, I didn't the definition. Small alpha and x smaller than beta. So every string is 0 p of x stochastic. So this is clear. Yeah, because if significance is 2 to the power, oh no, it's not so clear.
So first argument, you say alpha is complexity,
yeah,
and beta is
significance. So we need to bound the deficiency by Kolmogorov complexity. But it's not so clear if we have, so here 0, I mean O of 1. So if we only have a constant, then it's not so clear how to do it, because we only have a constant amount of bits to specify P of X. But if we make it a little bit bigger, then it is true. Well, if we allow log n bits, then this is, so if we allow order nicely, every string X is order log n, length of X, comma, P of X stochastic. Okay, it's clear what I mean. So, and now we can specify some P, some finite P. So how could we do it? So here is logarithm of the length of X. So we can use the length of X. No, it's still not clear. Sorry, bad question. I'm mixing up. This is enough. Let's say I'm using the, yeah, but this works. Okay. Now we can have, So which p should I use to prove that every string is order log of length of x and length of x stochastic? So the model p I use is uniform probability over all strings of a given length with the same length of x. So x is length n, we take uniform distribution. And then here we will have log 2 to the power minus n. Well, okay, we have log 2 to the power n becomes n minus complexity of x given p. So the distribution p just is a list of all n-bit strings, each time with value 2 to the power minus n. So basically here is n. So every string x is, but then the other side, every string x is also k of x plus O of 1 stochastic. Okay, and here we use the measure p that assigns all probability to x. And so then here this is bounded by a constant, and complexity of x given p is just also constant. But here it doesn't matter because it's negative. So then this is bounded by O of 1. So it's even negative. So I could write 0 here. Okay. What other simple properties do we have? Most string of length n. Okay. Next claim, most strings of length n are of 1 stochastic. So with probability 1 minus 2 to the power minus 10, or this fraction. So for every n, almost all strings of length n are of 1 stochastic. Is it right? No, it's not right. We need a model of order log n. But significant. So it's clear why. So which model we will use again to get this definition? It will be P will be so P will be uniform over n-bit strings. So then complexity of P again, order log n. And we know if we generate random string, then the efficiency will be bounded by O of 1. So most of the strings. What else do I have? Okay. So yeah, here you can put any constant you want, like 100 or 1 or 2. So if you make this constant bigger, so that if you place here, if you here place here C, then you have here C plus O of 1. Right? Because if you really want to hit all of the string, like you cannot hit all of the string because the all 0 sequence. No, yeah, that's also O of 1 stochastic. But I mean, with this proof, we use Pn uniform distribution over n bit string. All zero string is very non-stochastic for this distribution. So it means you pay here in the second constant. So you need to increase C, because when C becomes bigger than n, the all zero sequence is included in the proof. So okay, it's very logical. So I'm not trying to hard enough to explain it, because so there is a question: what about the C? It's clear or not? So with the C, it's not clear. Yeah. So so what is the proof? When we generate X randomly of length n, then we know that probability that randomness efficiency is bigger than C is proportional to 2 to the power minus C. Yeah. So oh, now it's okay. Yeah, but might be so the our proof doesn't work like this. So actually it's time bound, but it can be happen that for specific strings that randomness efficiency is big, but then for other Q, like we had with if there are a lot of zeros in the beginning or something, then we can make another measure P that has all zeros in the beginning, and this measure P makes the string stochastic. Okay, it's too philosophical. Let's not worry about this. Okay, there exists another definition of randomness deficiency based on sets. And so this definition is, let's call it D prime X. Here S is a set of strings, any set of strings. And it's equal to the logarithm of the size of S minus, okay. Yeah, that's why not. X given S. So finite set, S must be finite. So finite set, it can again be encoded as a string. Just concatenate in the prefix way all the elements. And randomness efficiency with sets and with strings, they are the same up to a logarithmic term. Well, there is a lemma. So d of x, sorry, we can define stochasticity. And so we can say that we can define stochasticity with sets. And then stochasticity is the same up to adding something.
Is it the same if they B as the
Yeah. So this is one direction. But first I need to write the statement correctly. So let us say that, so now I need a new definition of stochasticity. Say that X is alpha beta set stochastic if there exists a set S, A of S smaller than alpha, and D prime X given S is smaller than beta. So, and now is the lemma. If X is alpha beta stochastic, then it is alpha plus order log n And then I think here O of 1 is enough. We will need to check with the proof. Set stochastic. Here it is. Okay, and so one direction already stole the proof. So when we have standard stochastic, so if and only if, sorry. So if we are set stochastic, yeah, I need to write both directions. So this direction, yeah, okay, I will need to write a little bit. So if so the first direction is this one, and the second direction, if it's alpha beta set stochastic, then it is alpha alpha plus O of 1, beta plus O of 1 stochastic. And this is precisely like you say. So we add uniform distribution, and then we know that the logarithm is equal to logarithm of 1 over probability is precisely the logarithm of the set size. So this is okay. And now in the other direction, if X is alpha beta stochastic, then it is alpha plus ordered log n beta set stochastic. So now we have probability distribution, and we will get the set as follows. We will look at our element X and see what is the probability of X. And then we will consider the set of all the elements with the same probability up to factor 2. So for which the rounded probability. So actually the rounded logarithmic probability is the same as rounded logarithmic probability of X. So what does this mean? That we so the description. So should I write this? Should I say what is, yeah, okay. So let us define P of S, and let's call it K. Let's use small k. No, opposite. I need to define S. So S, K, and P is the set of all X. But I should not write here, right? So I can write it here. So S, P, and X is the set of all X for which logarithm 1 over P of X rounded up is equal to K. So here is our set. And number of elements in the set is K, 2 to the power K. And it's precisely 1 over the logarithmic probability. So if we compare the two definitions, we have log of size of S and log probability is precisely the same. When we go from probability to the set S, we drop information. So when we go up, so in this set P of X, there is less information than in P. And that means that this complexity can only become bigger. So the set deficiency decreases. So what I'm saying is that we've proven that with this model, relative to this model, set deficiency is smaller. Oh, fuck. I'm proving the other direction. No, I'm proving this direction. Okay, so I need to construct set statistics. Okay, and I managed to do it. So I proved so let P be an alpha beta stochastic, so complexity of beta is alpha. And so we understand that complexity of this set must be smaller than alpha because we can compute it from P plus the value of K, which is K must be smaller than length of X. So this is order log of n information. And secondly, well, it's smaller than 2n or something from the deficiency here. So yeah, logarithmic information and the deficiency can only be smaller because these are the same, and conditional complexity here can only be larger up to a constant. And so here we have beta plus O of 1. And this is very important observation. So we have some, so when mathematically definitions start to coincide, it's a sign we are hitting some important, something that at some point will be useful. And so here is our first sign. We can define it with probabilities and with sets. And I will prove one property, and we will see like 6 definitions in this lecture that leads to the same notion of alpha beta stochastic. So when we fiddle a little bit with the parameters, when we make logarithmic changes, we will each time get the same notion. Yeah. And so we can define alpha beta stochasticity with probabilities, and here is a definition.
No, I mean, yes, the proof.
This is not clear yet. So it's alpha beta stochastic. So we have some measure P of complexity at most alpha and deficiency beta. We need to get a set with complexity at most alpha plus a bit more, and stochastic and deficiency beta plus at most a constant. So here is the set. We look at all the strengths X that have approximately the same probability. Okay. So now we have to check that deficiency. Okay, so complexity of S is computed from P and the single number K. So K cannot be too big because deficiency okay, I didn't say explicitly, but it doesn't make sense to choose beta more than n here. So we will always use, let us always assume alpha is at least 2 log n or something, so that we can, if alpha is at least logarithmic, then we have that every x is alpha and stochastic, alpha length stochastic. We discussed it in the beginning. And so we can just, it only makes sense to speak about beta. So we can assume that beta is smaller than n, because it's always true for beta equal to n. So we can take small beta. So we can always decrease beta in this statement, and it will remain true. So I'm just saying that we just, to specify k, we just need logarithmic number of bits. Because here we can assume beta is small in the assumption. We can always make it stronger and then prove something stronger here. Okay, sorry, I'm distracted. So yes.
So with P, we find the K to the complexity of.
Yeah. So we hard code the K inside when we compute S. And then we use the code for P to list all of the X's in the set. So so this satisfies complexity bound. Now the deficiency bound. So we have to prove that D prime is smaller than D. So then let's look to the first term. Log S must be smaller than log 1 over P. because there can be at most 2 to the k elements satisfying this order 2 to the k elements. So this is equal to k by definition. This is at most k plus 1 by construction. So k plus 1 is enough. And then we have to compare this and this. So in S has less information than in P. But there is k here. We added k. So there is indeed, I do need this logarithm here. Okay. Yeah, it's unavoidable. So yeah.
Again, why the algorithm?
Because here P is in the condition. And so S, so when we go from P to S, what did we do? We add the description of K. So the code for S contains description of K. And otherwise, it takes information from P. So after we add the K, we have to understand that here can be more information. But also there can be less information because it might not be possible to reconstruct P from, so given S, we might not be able to reconstruct P. So in this sense, it helps us. Okay, this would catch. There was some error, but now it's fixed. But it's one more time.
Well, I don't get why we paid it.
Why we added this. Yeah. Okay, so we have to compare these two terms. And so imagine that to compute S, we only need to know P. Then we can just have O(1) information. But there was a small hiccup here. To get S, we need to know P, but also K. Actually, this is confusing. Yeah.
But this K comes to P and K would be like.
Yeah. So if you know X and you know P, then you get K. That's true. But here is a problem. So this is in the condition. It's before we know X. Okay. Now there is another fundamental question. We know that if we apply a computable function, Kolmogorov complexity cannot increase. And so we have, okay, I will remove set statistic. We won't need it for some time. Well, we know that complexity of f of x is bounded by complexity of x plus O(1). Can we say the same thing about alpha beta stochasticity? If we apply a function, is it true that it's still alpha beta stochastic after increasing by constant? And the answer is yes. So here is lemma. Let's write it somewhere else. So we don't need it. So if x is alpha beta stochastic, then f of x is alpha plus O(1), beta plus O(1) stochastic. And so to prove it, we will use the second definition. And so we will use, so remember about prefix complexity. So this conditional complexity, we understood that it was the maximum measure up to O(1) that is Laurent semi-computable and for which the sum on the first argument bound to 1. So we looked at all semi-measures that are Laurent semi-computable and we said that measure M was the maximal one. So discrete a priori probability. And that's the definition that we will use. And so we will tolerance proof. And then so first I will say what is the model. And so here f is computable function, not it must be total function. So f is total and computable. So now before with Kolmogorov complex, it was enough that f was a partial function that's computable. Now this is no longer true. In the proof, it's important that f is total function. So and so now let us say what is the statistic. Statistic will be f of p. So what means f of p? So you've seen this before. What happens if you apply a function to probability distribution? And so the f of p probability of some string y is equal to the sum of all px y f of x equal y. Sorry, all x for which f of x equals y. It's clear what it means, so and we remap, and then the stochastic, the statistic will be f of p. Here is lemma. So what we have to prove is that so we will. So clearly, complexity of this statistic can only be smaller. And so because if we know f, we can compute this measure. Sorry, if we know p and f, we can compute this new measure. And so f is a fixed function. So of one constant depends on f here, but not on p. So a fixed procedure we can perform. So we understand that f of p, complexity of f of p is smaller than complexity of p, is smaller than alpha, and all up to alpha. And now we have to check that the randomness efficiency is smaller. So we have to check that d of f of x given f of p. So this is what remains to be proven, is smaller than d of x given p. And by the way, where should I stop writing? It's yeah. Can you just say it? So where is the forbidden?
Over just
Yeah, but there is still person behind you. So here I can still write.
Yeah.
Here, no, and I can start writing here. Yeah. No, not for you.
It's okay. It's okay.
Yeah. So here is forbidden. Ah, here I can write again. I have some. Okay. So that's what we have to prove. This I definitely can. Yes. Okay, let us expand the definition. So in the right hand, so let's just expand using this characterization. So in the right hand, we have mx given p divided by p of x. And here we have m of f of x given f of p divided by f of p of y, of f of x. Okay, this is very ugly. So I will put P of X, I will move to the right side. And then I will compute the sum over all X. Okay, by the way, so left hand, no, too early. So this is what we need to prove up to of one factor. Up to before I use the star notation to get rid of one factor. So I will put P of X there. And so we have P of X divided by f of P of f of X. And then there is m of f of X given f of P. This is very ugly. And I need to prove that this is smaller than m of X given P. Okay, and now I claim that when I sum the left-hand side over all the x's, I will have something bounded by 1. And this is, okay, so, and why is it true? So I want to sum here over all x's. And so in the sum, I can collect the x's. I will collect over all the values of f of y. So I will first sum. So here I need to sum over all the x's. But I will do it in a special way. I will first sum over all the y's, and then all over all x's, such that f of x is equal to y. And now there is good news, because when I sum over all these x's, so I can simplify a little bit. Wherever I see f of x, I can write y now. So let us make our life a bit easier. So here I have y and y. And so now I have another task. So let us forget about this. Now I take the sum. And so I want to prove that this is smaller than 1. Okay. So what is f of p of y? So remember, what is f of p of y is just the sum over all p x's for x's that go to y. So what we have here, this will, so we sum over all x's that go to y. And when we look to the numerator, we have precisely the denominator. So this all cancels. And this is very good news, because now only thing that remains is y here. So when we evaluate first sum, we could place brackets. And what is inside the brackets is beautiful 1. So it poof, disappears. And it's by this annoying definition of y. And so this is annoying definition of f of p. It's just the sum over all p of x where x goes to y.
So it's not 1, it's multiple.
No, it's exactly 1 because of this definition. So if you put a sum in the numerator, you have precisely the definition of the denominator. Yeah, it's so easy and so perfectly 1 that it's surprising. So this all disappears, and we have sum over y, and y given something. And we know sum over conditional probability in first argument is at most 1. So what we have proven is that here this terrible thing is a semi-measure, a conditional semi-measure. And so I should now remove the sum again. So I hope this step is clear, because I will delete what we have done here. The sums are gone now. And so I delete this to avoid confusion, but now I need to put the y's back. So we have f of x here and f of x here. So now what we had before is restored, but we know something new. We know what here is a function of x and p. And we know when we sum over all the x's, we have at most one. So we have a conditional semi-measure here. And we know that, so this is a function that depends, so we can say q of x given p is equal to this thing here. We know that q is a semi-measure. We also know that q is Lauer semi-computable. Why? Because this m is Lauer semi-computable and this ratio is computable. And here it's important that we use that f is total computable function. So it's defined on all the arguments. And we also need that p is as finite, finite support. So it's defined only for finitely many strings. And is rational and so on. And all these things together, they ensure that this ratio is computable. And hence q is Lauer semi-computable. And so we understand that since q is Lauer semi-computable semi-measure, it must be smaller up to constant than mx given p. And so there is intuitive property. So if we have, okay, let's first guarantee that the proof is understood. So we use that if U is a Lauer semi-computable semi-measure, then Q x given P, so P as a string basically, must be smaller up to a constant than M given x of P. So that's the property we use. So is there a step you want to ask about? So we have inequality from this, and here we assume that Q is semi-measure and it's Lauer semi-computable. So there can be only problem. Okay, so assume you agree that it's Lauer semi-computable and it's a semi-measure. You agree that we conclude as an inequality. And then you need to remember that this inequality was precisely saying that this deficiency is smaller than this thing here, up to O of 1. So there was plus O of 1 here. But this is okay because in the lemma we have O of 1 here. So, okay, so when we have Q, so these two properties, semi-measure and Lauer semi-computable, then we are good. Okay, so let's now check that we have Q is semi-measure. So for this, we have to check that for every P, when we sum over all the x's, we have something bounded by 1. And this was this beautiful property when we insert it. This was okay for, I think.
And how
we check that it's Lauer semi-computable.
no, it's clear how we transit from this inequality to the left one.
From this one to here. Yeah. Okay. Then it's this. So so here we just put P in the front here. And then we have this one. So you ask how we go from here to here. And here is the second definition of randomness deficiency. On the right, it's defined in this way. And then, yeah. Okay, so cool. So now you understand that. So it basically says if we understand all regularities in X and we apply computable function, we are guaranteed to understand all regularities in the argument. Okay, and this is all I wanted to say about randomness deficiency. So there is a whole research area of people that like to study randomness tests, but they study it for infinite sequences. So Kolmogorov was wanted everyone to study finite strings, and then Per Martin Löf came somewhere in the 60s, and he would later become famous logician, and he made a definition for infinite sequences, and then everyone started to study infinite sequences. And so there are people who told me that Kolmogorov came and say, why don't you study finite sequences? And they make all these books, complicate. There is like 2 books all about such randomness tests and different ways to get them and relate them. And it's still, okay, it's interesting, but not so clear. So, and then it reappears in reverse mathematics, but most important work, only few people think about. I mean, most important for application is about finite strings, it seems. But still, I think this theory all is not yet understood, how it relates to applications. But okay, I will read much more. So there is a thick book by Risanen and Grunwald about minimum description length principle. And so it's time we will go there now. So, okay. So this is randomness deficiency. There exists a second way so there is a very philosophically different way to say that a model is good for a string. And that is that to say that the model is part of a shortest description for the string. So it's a much stronger condition. This is actually the main thing that you need to understand for the question in the colloquium. So it's called optimality deficiency. So there is dx comma p. It's called optimality deficiency, and it's equal to. Let me first say what it is. This x. No, not k of x. It is k of p plus logarithm 1 over p of x. So again, arithmetic coding or Huffman coding minus k of x. So deficiency of x given model P is small if P is a part of a shortest description. If you can obtain a shortest description of x using the measure P. And so for every x, there exists a measure P for which optimality deficiency is 0. So the claim is that for every x, there exists P, such that optimality deficiency is bounded by of 1. Okay, you can say there exists C like this. And this is the singleton model. And so just a model that assigns all probability to x, it will satisfy this property. So, and this is, so Kolmogorov then said that the best model will be the P of smallest complexity that satisfies this, that has small optimality deficiency. So you can pick some reasonably small C and then think, what is the best P that gives this thing? So we want a simple measure that assigns high probability to X. So we can think about, imagine you have a sequence of So I'm trying to think about an example. So in MDL book, but it's a bit of annoying because it's a continuous real variables. And so they say the model will be the set of coefficients of regression function, and the probabilities will be how far you deviate from your trend defined by these coefficients. So for example, if the training set is a pair x1, y1, so let's use a1, v1, argument and value, and so on. So x is like this, a l v l. So it's a training set. And then they say, okay, let P be defined by a regression function, and we assume Gaussian noise with certain sigma around it. And so P will be normally distributed with average. So there are some coefficients, alpha 1. Let's say. Or just think that inside r times r to the power now. So, and then you can have some polynomial of a, and then some standard deviation. Okay, this is continuous measure, so you need to discretize, need to like consider finite precision and have some bins and so on and so on. And so the idea is that the measure p of x is equal to okay, and then there is a product. Anyway, it's very long to give an example, but the idea is that the more complex you make your polynomial to encode the trend, the bigger is this complexity. But the better you make your trend, the more you can hit, the more you can decrease the sigma and still have high probability. Well, yeah, so the higher is your probability. And so there is a trade-off. If I take a complex model and you want a high probability, so if your polynomial is complicated enough, you can fit any sequence of data. So if you hard code the p, so this is the extreme case where k of p is equal to k of x. And this probability is basically 1. But the best p is the one that takes as little information as possible, but still reaches Kolmogorov complexity. So it decreases the chance to overfit. And this is the idea what these people with neural networks use. They say, okay, there are weights in the network. And what they sometimes do is they do weight regularization. They add a square of the values of the weights to the objective, especially if it's small neural net. So there is weight decay or something they call it. And so ID comes from here. And people in MDL says that normally there is a parameter that tells you what's the weight for weight regularization, and they train it with cross-validation. And then there is a whole area of MDL people that say, oh, but we use compression to avoid tuning the weight of the weight regularization. So the parameter of the weight. So there are two objectives: make probability high and make the squares of all the weights in the network small. And so in this Hinton paper, they use a little bit more complex. So there is some mixture of Gaussians and so on, but the idea is the same. Okay. And so now we can ask, what is the minimal complexity for which the optimality deficiency will be small? And it turns out that this is the same as the minimal complexity, minimal alpha, for which string is alpha beta stochastic. So it turns out that two very different philosophies will select approximately the same models. Well, this is not completely true what I'm saying. I'm just saying that, so here we have a stronger, so first let us compare the two conditions. And I was stupid enough to delete the definition. So there is an easy observation. If we have a model that satisfies this condition, then we know the randomness deficiency is small. So there is a little lemma. It says that randomness deficiency of X given P is smaller than optimality deficiency of X comma P plus, I think log N is the, yeah, so we will, this follows from symmetry of information. Turns out that other inequality is not true. This will not be true. However, we can make a transformation on the model for which it becomes true. We can get rid of some information. So here, in randomness deficiency, so what does it mean? So dx given p is equal to, that is, okay, that log 1 over p of x minus kx given p. Note that if here we add information to p, irrelevant information, some randomness that not connected to x, then this term will not change. But in this definition, if we add to p irrelevant information to x, this will be violated. So that means some models that are good, that have zero randomness deficiency, will be bad in this definition. But it turns out the other way around is not the case. So let us try to prove it. Let us try to prove this inequality. So, and it's a consequence of symmetry of information. So let us expand the left-hand side. So we have log 1 over p of x minus k of x. Okay, well, I still have it here. And so we want to prove that this is smaller than kp plus log 1 over p of x minus k of x. So we can cancel this and this. And so what is left, if we reorganize it, is kx given p plus, no. We have k of x smaller than k of p plus k x given p. And so this is equivalent, so it's okay. And so here we have, so this is true up to logarithm. And so if I add here plus order log n. Oh, no, this prefix complexity, so I just can add all of 1. So for prefix, we can concatenate programs. So this is okay. So in other words, we have proven this thing here. I just had to rearrange it and apply a concatenation of programs. So now we already understand why the other inequality does not hold. And because we can understand if we add things to p that are irrelevant for x, then this increases, but this remains the same, but this one significantly increases. So now is the question, can we go in the other direction? But this is a bit hard question. So let me think what I should. So it will take like, I need to define a complexity profile. And so then in the colloquium, there is explicit construction of minimal sufficient statistic. So I will, I don't know yet if so I will need to speak for 20 minutes more if you're not too tired. And then we will see if we manage to, if it somehow easily follows easily from explanations, then I will explain this. But let's first focus on the thing that we're planned for colloquium. Okay. So now we can define, so let us say what is IJ code. So I will, so again, we can define optimality deficiency not with probability, but with sets. And again, it will be equivalent for the same reasons. So we can transform probability in the same, so from set, we have probability by uniform distribution and vice versa. We do the same thing. So let us now define optimality deficiency. Oh, sorry, actually, I don't need this. This definition. And so we can look through an I star J code representation of X, sorry. A star J representation of X. And what is it? It is a set of complexity at most I with cardinality 2 to the power J. So an X containing set with complexity at most I and cardinality 2 to the power J at most.
What is the cardinality?
It's a number of elements. Yeah. Of X. So this is the definition. Is a set S with 3 conditions. So X is an S. C of S is bounded by I. Now, from now on, everything will be up to logarithms, so it doesn't matter if you use plane or prefix complexity. And finally, there is cardinality of X, S, is bounded by 2 to the power J. So number of elements. Okay. And now we can define the profile. So the profile P of X is all the pairs for which there exists an IJ representation. IJ exists representation. So this is a set that's like, if there is a point in the set, then all the points on the top. So here we have I and J. So this is a set and it's of the form. So here we have K of X, C of X. Here we have C of X. Let me write this better. And then the set will be something like this. And that contains E. So this is complexity profile of X. So, and what we notice here is that we will look at the boundary. And so the idea is that the set that describes everything will be the smallest point And so the best model to describe X will be the first point where we hit this line of complexity. So the two-part description here is so if I plus j is bounded by C of X, everything is up to order log of n. So here, plus something small. So the smallest I for which we hit the boundary here will be a minimal description of X using the set S. And so the program will be a program that prints S plus the index of X in the print of X, maybe as a sorted or something, lexicographic index. So this is the model that gets all the regularities. So in the example with zeros and odd bits, it will be just a string with even bits. Okay, let's continue. So and here let's look to the boundary. Well, first we understand that point 0 and C of X is always in the set that correspond to the singleton set containing X. If we start in log n, then here we start with so the point n of one, the same observation is also in this graph here. And the claim is that the slope goes down faster than with slope 1. So you go down with slope negative more than 1. And why is this? So why do we go down faster than with slope 1? Well, it's just clear. So let us look to a given set that satisfies condition. Complexity is small, and what can we do? We have a set. We can, if this is our set, we can put it in equal blocks. So if we divide S in 2 to the power a prime blocks or something, then each of the small sets has complexity a prime bits more to specify. Right? So if we have a program that says what is S, then we can define a smaller set by adding. So what I'm let me what I'm saying is that if X has so if there is I star j representation, then there exists I plus C star j minus C representation. So that's the claim. So how do we prove it? And so if you have ij representation, there is a set S of complexity I, according to satisfy all these conditions here. Now we will create smaller sets. So let us make sets T1, T2, and so on, T to the power 2 to the power C. So we divide S in roughly equal sets. And then the complexity of each set, I need some index, TE, is bounded by complexity of S plus C, plus order log C. Right? Because we can say to specify one of the sets, we just have to tell which block. So we split S into blocks of equal size, we specify the block. And so the size is 2 to the power C fraction smaller, and the complexity is C bits more. And so this is the proof that this line goes down smaller than, so for every point, the line here is in the set, but the line could go down faster. Okay. What else is there to say? So there exists. So there exists a theorem that says that every complexity profile that satisfies this criterion, so in total we have 3 criterions. Point n0 should be there. Point k of k0 must be there. And it should be, if a point is in it, then the line starting there going with -1 should be there. And so every shape of the boundary is possible within these 3 constraints. But I will not prove it because it's too much. I've already spoken too long. So the last thing we have to do is present explicit construction. So people manage to construct explicit minimal sufficient statistic and then abandon the theory, because they realized that all the minimal sufficient statistics were the same. And so this idea of extracting useful information didn't make sense. However, these MDL people, they kept using this happily. And so the theory was changed like 8 years ago. Vereshchagin wrote a paper where he added an extra assumption on the model. And then everything becomes normal. So there is a chance that if you add one more assumption, and so he take a very simple assumption, it means that there exists a computable function, and so given x produces p. He says, like, okay, when you want to extract information, you will use a computable function. Let us require the existence of this model here. And then the previous property is destroyed. But still, in theoretical consideration, this property is, but okay, maybe it's kind of negative message. I can drop it from colloquium because it's maybe not so useful to put it, but it's kind of like surprising, beautiful construction. So how, okay, I will tell it, but maybe I will change the question for colloquium to something that we said. So I can like add the question about information non-increased, because I know that you now very well understand this. I mean that if you apply a computable function, then alpha beta stochastic string remains alpha beta. So I will change the question to this question. And then I will explain. So there is a theory by Chaitin that says that if you know one certain number, then you can prove all theorems in mathematics. So there exists 1 kilobyte, and if you know this 1 kilobyte of bits, you know you can in principle compute all the answers for all theorems whose statement required less than 1 kilobyte. And so minimal sufficient statistic consists of this number. You could also solve the halting problem for all programs of length less than 100 kilobyte. And so this minimal sufficient statistics is closely related to this number. And this means that all the strings have essentially the same minimal sufficient statistic. So they're all prefixes of the same special string. And to define the string, so we will consider a special number. So there's the number nk, and it's equal to the number of strings x, for which complexity is smaller than k. Okay, and so I will use with set description. So I need to be a bit more careful. I will use n, and I require that the length of x is equal to n. So if you know this number, you can solve the halting problem on all strings of length, for all programs of length at most n minus a little bit. And so here, but sufficient statistic with set S. So the S definition. So in the S definition, here we have logarithm size of S, and here A of S. So definition is defined by a set S. Right? So how can we get the set from this number? And the idea is to look to the binary decomposition of this number. Power Z, so where A is bigger than B is bigger than. So there exists an enumeration. We can enumerate all the strings. If we know N and K, we can enumerate all the set. And so now we can put them inside blocks. So we can consider SA. It consists about the 2 to the power A. Oh, let's do it opposite. So let's do it like this. So Z is the smallest number. So SA will be 2 to the power A first strings. As B will be the 2 to the power B next strings. As C is, and so on. So here we define all sets. And it turns out that these sets are the minimal sufficient statistics. Okay, so if a set S satisfies this property for the minimal sufficient statistic is just the model for which you are reasonably close to this line. So sufficient statistic is any set S that gives you a point near this line. It's called sufficient. It comes from statistics. This idea, sufficient statistic is it's for estimation, or you extract all what you need from the data. But here there is no target. But the idea is that all useful information is inside this model, and all the remaining thing is noise. And so there are experiments that try to estimate this function for denoising of images. So that there are images with rain, and then they try to find the statistic. And the hope is that the rain is taken out and you can send only the image without the rain. And then the receiver just knows that he should insert the random places of the drops. And then you can send a picture with fewer information, but with using randomness. So this is idea why it's called sufficient statistic, while there is no specific estimator. So there is this slightly crazy idea. Okay, but this is like what is a philosophy, but in practice, it turns out that these sets, so there are just n sets, and every set of every string has one of these sets as minimal sufficient statistic. And then there's a question, can we prove that these sets are indeed the minimal sufficient statistic? So can we understand that these sets, so X will always be in precisely one of these sets. So remember what we did. We fixed an enumeration of all the X's that satisfy this condition. And so we defined as A to be the first two A elements, then the next two to the B elements, and so on. So X will be in precisely one of these sets. And the claim is that this set is minimal sufficient statistic. And so if you take any two strings, then first string, then one of these strings its sufficient statistic as a prefix of the other one. Okay, by the way, what is the complexity of these sets? And so so what is complexity of SA? No, that's very easy. You just need to know what is A to enumerate SA. And this is similar. So if you So to enumerate, so we have C of Si. So complexity of Si is smaller than I plus O of 1. Well, you need to know N and K as well. So Sa is smaller than I plus order log N. Well, then just the complexity to store K and N. And so what is the reason? And so we look to a number in binary here. And to understand what is, so 2 to the power I, we just need to know this number here in binary. If we know this number in binary, we enumerate all the big sets until there are fewer than 2 to the power I strings left. And then the next block of 2 to the power I strings is precisely our set Si. So I actually, you need to know the previous and the previous one in the number. And so here we have CSI is smaller than I. But we also know that the size of Si, the logarithmic size, is smaller than N minus I. Because we know that the last set is about 2 to the power minus N size. And when we have, so when we fill the I bit, yeah, it's like a bit annoying to explain, but there's just a number in binary. And yeah. So the difference between, so there is a number 1, 0, 0, 1, 1, 1, 0, 1, 0. So what we are doing here is the size of the set is 1, 0, 0, 0. Right? So if I is equal to N minus 4 here, so in the form. So if this position is the ith position, so here is 1 and here is N. So then we enumerate the number and our set Si starts when we reach the number 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. So this is the first string in Si. And the last one is 1, 0, 0, 1, 1, 0. The last one is 1, 1, 1, 1. So that's our last string. And so the complexity to store this set, we need to store these bits. And the number of bits is 2 to the power of this distance, N minus I. And here, this distance, this I. Okay, and so this is explicit construction. And so this number that says how many strings have small complexity, it's magical number. It turns out that if you know this number, then you compute this and vice versa. Okay, but I spoke again almost 2 hours. So let's take a break now. So there was a seminar question. And okay, maybe we can just do the first exercise and then go home. Since these exercises, 2 to 4 is more an exercise on constructing minimal sufficient statistic. But since I will drop it for colloquium, maybe we can drop the exercises as well. And just to 8.1. I think everyone has a lot of work. So